Hello, good morning, and welcome to this presentation. So we are in the sixth lecture, that is Shannon-Fano encoding. So this Shannon-Fano encoding is again a variable length coding algorithm. So in this case, we combine Shannon's method as well as a Robert Fano's method. We have some differences that you may notice during the when we analyze this Shannon-Fano encoding. But we will right now dive into the Shannon-Fano encoding algorithm. So the process here consists of different steps. So given a source that emits different symbols and also their probabilities, then how can we use a Shannon-Fano encoding to encode the given message? That's the activity here in case of Shannon-Fano encoding. So the different steps of Shannon-Fano encoding consists of first, we have the symbols that should be arranged in the non-increasing order of probability. So right now we have different symbols and also we know their probabilities. In that case, we should arrange them in the non-increasing order of the probability. Then in the second step, we divide the symbols into two groups that are nearly equiprobable. That means since we have a list of symbols and their probabilities, we divide all the symbols into two groups so that one group will have some symbols and the other group will have remaining symbols. So the division of this group should be done in such a way that the probability that is in the first group, the sum of the probabilities, and the second group, the sum of probabilities should be nearly equal. So then in the third step, as we have already done two groups, distributed all the messages between two groups, the first group will be assigned a 0. That's a top group. And the second group, that's a bottom group, what we call, that will be assigned a 1. So these are the codes we assign as we go on with this coding technique. So the top group is assigned 0 and the bottom group, the other group is assigned 1. And this process will continue. That means we keep doing the groups until no more groups can be formed. So in the second step, what we did is we formed two groups and we assigned a 0 to the first group and 1 to the second group. And then in the fourth step, what we are going to do is we just repeat the same process. I mean, maybe the first group, can it be divided again into two groups? Whether the second group, can it be divided again into two groups? We keep checking that. If it is possible, we will continue to do the second step. I mean, we again divide it into two groups and assign the top group as a 0 and the bottom group as 1 and so on until no more groups can be formed. So finally, whatever codes we get by assigning 0 and 1s to all those groups in each of the steps, that will be the code word for each symbol. So these are the 5 steps of Shannon-Fano encoding. So these appear in general, but if we have an example, we would be trying to understand more in detail. So let us see an example here. So in this example, it says a DMS, that is discrete memoryless source, produces 4 symbols as 1, 2, 3, and 4. And they have a probability of half, 1 by 4, 1 by 8, and 1 by 8 respectively. In that context, construct a code using Shannon-Fano encoding algorithm and also find the efficiency of coding. So for the first task here is to construct the code using Shannon-Fano encoding. So for Shannon-Fano encoding, what we need is nothing but the symbols and their probabilities. Since we have them already, we just need to apply the previous steps here. I mean the steps of Shannon-Fano encoding, what we studied earlier, we need to apply here. So let us begin with the first step, that is sort the probabilities in the non-order. So here, first we have the highest probability, and then we have the lowest probability. So these are the sorted probabilities. It happens that in the question itself, we have the required information that's in the sorted order. Otherwise, we need to sort it. Okay. Then in the second step, we need to divide them into two groups, right? So we have the four symbols S1 to 4, and their probabilities varying from half to 1 by 8 as given here. And in the next step, we need to divide them, all these four symbols, into two groups such that the sum of probabilities in the two groups are almost equal. So what would be the division? Where would be the division boundary? So if you see here, if I consider 1 by 2 and 1 by 4 as one group and remaining 2 as one group, then the total probability here, 1 by 8 plus 1 by 8, that is 1 by 4. But the probability here is half plus 1 by 4, that is 3 by 4. So this is 3 by 4, and this group becomes 1 by 4. So they are not equal, right? They are not even nearly equal. In that case, that is not the right way of dividing. Okay, let us consider another setting. For example, I will have the first element in one group and all the three elements in another group. Then what would be the probability here? 1 by 8 plus 1 by 8 plus 1 by 4. That is 1 by 2, right? And the top group here, its probability is also 1 by 2. So it looks like that here the group 1 and group 2, they both have the equal probability. So this is the right way of dividing the symbols into two groups. So from this discussion, in the first stage, we will be forming two groups in this way. So in the first group, only one symbol. In the second group, there are three symbols, because the sum of the probabilities here becomes 1 by 2, and the total probability here is 1 by 2. They are almost equal, or exactly equal in this case. After this, the next step is the top group will be assigned 0 and the bottom group will be assigned 1. That is what is the third step in the Shannon-Fano encoding algorithm. So the top group is assigned a 0, the code word, and the bottom group is assigned a 1. Yes. Now can we continue this? That is, can we form further groups from this set? Of course, if you see the top group here, we cannot divide it because there is only one element, we cannot divide it. But if we see the bottom group here, it looks like we can form into subgroups, again two groups, because there are three elements here. We can divide it into two groups. How to do that? Okay, let us see here. Again, we need to follow the same principle. That is, when we divide these three elements into two groups, the sum of probabilities in both the groups should be almost equal. For example, here, let us have this element in one group and these two elements in another group. So the probability here is 1 by 4. The total probability here is also 1 by 4 because it's a sum of 1 by 8 and 1 by 8. So that's the right way of dividing this further. We will see that, or we will call that as the second stage. So here, for the second stage, we have three participants and we need to divide it this way. So when I divide it, this element, it is here, and these two elements in one group, that is combined here and written here. So now you'll see how to assign the code words here. So the red color indicates the earlier stage code word, because in the earlier stage, these three elements had a code of 1. So that will be carried forward here, 1. the red color. And right now, the upper group will have a 0 and the lower group will have a 1, as done similarly in the first stage. The first group, the upper group had a 0 and lower group had a 1. So that's what the Shannon-Fano encoding algorithm suggests. The top group will have a 0, bottom group will have a 1. So this is what the coding assigned in this stage, second stage. All right, can we continue this further? So if you see here, the top group has only one element which cannot be divided again into two groups. The bottom group here has two candidates, so we may divide it into two groups. So of course the probabilities are equal, so we can easily divide it into two groups. So we will do that in the next stage. So this is called as the stage 3. So in this case, we will divide this group into two halves because the division is possible. Okay, so the first division is here and we will assign a code to that. And the second division is here and also we will assign the code to here. So now this 1 1, because we are dividing this group here, so 1 1 is the code carried forward from here to here. So we have a 1 1 here as well as 1 1 here. And in this stage, stage 3, we have to assign a 0 to the top group, that is in green color here, and we have to assign a 1 to the bottom group here. So we have assigned that. So if you see carefully, no further divisions are possible because every group has only one element. We cannot divide it further. So this becomes the end of the Shannon-Fano encoding scheme, where no further division is possible. So in the in the fifth step of Shannon-Fano encoding, we have the code words here. For example, the last symbol. So this represents the last symbol S4. So that will have a code word of 1, 1, and 1. And the third symbol will have a code word of 1, 1, and 0. Similarly, the second symbol here and the first symbol here. So if you notice this, every symbol has a different code word length. I mean, they have a variable code word length. So this is the idea. So basically, this should be the fifth step because we have combined many things in the previous step. So in this step, we have uh, the code words as shown here. For example, the different symbols and probabilities and the code words what we have discovered in the previous step, and NI here indicates the size of the code word or the length of the code word. For example, it's 1 here because there is only one bit. There are 2 bits here, that's why NI is 2, and similarly 3 because there are 3 bits here. So NI indicates the length of the code word. So this is how the Shannon-Fano encoding operates. And the next question in the example was to determine the coding efficiency and also the average code word length. So right now we will determine the average code word length, that is denoted as L. L is equal to summation of Ni and Pi for all the symbols. Right now we have 4 symbols. So to determine the average code word length, this is the equation where we will be multiplying the probability with its code word length. So basically this is nothing but weighted probability. So Ni comes from this column here and probabilities are listed here. So now it becomes very easy to compute the average code word length. So for the first symbol, code word length Ni is 1 and its probability is 1 by 2, and for the second symbol, third and fourth symbols here. So that becomes 1.75 minutes per symbol. Next, we find the entropy of the source. We are very much aware of finding the entropy. Entropy is nothing but the summation of pi log 1 by pi. So summation here is for all the symbols to be transmitted or encoded. So we know the probabilities. You can easily find the entropy. So 1.75 bits per symbol. So we are left with the coding efficiency. That is what the question was, to find the coding efficiency, eta c. That is nothing but the ratio of h of s, that is the entropy, and L log R. L is the average code word length, and log R, here R is a value, the value of R is 2 if it's a binary coding, or it is 3 if it is ternary coding, and so on. So generally we use by default as binary coding 0, 1. So R value is 2. So this is log base 2, and the value of R is 2 for binary. Okay, so since we know all the values here, we will find the coding efficiency is nothing but 1.75, that is h of s, divided by L multiplied by log of R. R value is 2 for binary, and the log of is log 2, log base 2. So log 2 base 2 is 1. So this is nothing but 1.75 divided by 1.75. That will lead us to 1, or 100% efficiency. So the coding efficiency of this particular example is 100%. So this is how we apply the Shannon's Fano encoding and determine its coding efficiency. So this is one example. But if you notice that there are different ways, there could be different ways of grouping the symbols. So we will see in one of the examples what would be the effect in such a case. So we will go to the second example here. So this example is a DMS source that has alphabets varying from x1 to x5. There are 5 different alphabets or symbols. Each has a probability of 1 by 5. In that case, construct a Shannon-Fano encoding scheme and find its efficiency. The second question is construct another Shannon-Fano code and find its efficiency. So now, in this case, we are trying to explore the different ways of grouping. Because since there are 5 symbols here, can we group these 2 together and these 3 together? Or can we group these 3 together and these 2 together? And what's the performance? Or maybe all 4 in one group and just one element in one group. So there are different ways of division possible. So based on that, I mean, we of course we need to consider the probability values. So based on that, how can we determine the grouping style and the coding efficiency that we will see in this example? So here in the first part, we will try the first step here are the listing of probabilities in the non-increasing order. For example, these are the 5 symbols here varying from x1 to x5, and these are the probability values here. The probability values are equal for all the symbols. So probability values are 1 by 5 or 0.2 for all the symbols. So they are already in the sorted order. So in the next step, what do? We need to divide them into 2 groups. These 5 symbols we have to divide them into 2 groups such that the probability values are almost equal. So if you consider here dividing it as so since we have already done all the steps here, so right now we will try to see what is done in this case. So here we have considered 3 symbols in one group. So the total probability is 0.6, and remaining 2 symbols in another group. So the total probability becomes 0.4. Because we cannot divide here these 5 symbols equally as 0.5 and 0.5. like we did in the previous example, because there is no way of distributing these elements into two groups such that they have the equal probability. They are almost or nearly equal. So this is zero point 0.6, this is zero point 0.4. That is what the Shannon's-Fano encoding says. Divided into two groups such that their probabilities are almost equal. They need not be equal. So let us make one group here that has three elements and their probability value is 0.6. Let us make another group here using these two elements and their probability value is 0.4. And then you may also think that we divide these two as one group and these three as another group. Of course, that is possible. That is another way of uh, forming the groups. This is one way, okay? So let us go with this way. So we have three elements here. So we will assign all the three elements with a code of 0, top group, and the bottom group will have a code value of 1. Right, next we'll go to the second stage. In the second stage, we have in the top group, we have three elements. Can we divide it further? Of course, we can divide it further. Whether one element should be in one group or two elements in one group, that's again, we have choices here. So in this particular case, we have divided the top element, the first element here as the top group, and the remaining two elements from this group as the bottom group. Similarly, the we have two elements in this group, we again need to divide them into two groups. So the first element goes to the top group and the second element goes to the bottom group. And then we will do the coding here. So you may notice here, this group or the elements in this group have a code of 0 in the first stage. So that will be carried forward in the second stage also. Here, 0. Because these subgroups are formed from this particular group. So that 0 is maintained here. And in this particular stage, that is stage 2, the top element will have a value of 0, the code value is 0, and the bottom group will have a code value of 1. That is what's shown here. Similarly, among these two groups, they emerge from the division of this group. So it had a value of 1, so that value is listed here. And the top element will have a value of 0 and the bottom element will have a value of 1. Okay, so if you notice here, these groups cannot be further divided. Similarly, this group cannot be divided, but this group has two elements, so we can try to divide this into two groups. So that is done in the next stage, that is stage 3. So we divide this as a top group and this as a bottom group, and we will assign the code words here. So the code word is 0, 1 in the previous stage, that is carried here 0, 1 and 0, 1. But in this stage, we are assigning a top group with a 0 and bottom group with 1. So right now we have all the elements being divided as individual elements and no subgroup formation is possible. So right now we also have all the code words. Okay, they are listed here. So we had the 5 elements here, their probabilities, and right now we have the code words. For the first element it was 0, 0. If you go back and see here, for the first element it is 0, 0. And for the next element it is 0, 1, 0. Similarly for the fifth element it is 1, 1 and so on. And now here Ni indicates a code word length. For example, here there are 2 bits, that is 2, 3 bits, that is 3, and so on. So this is how the Shannon-Fano encoding is done. And then we need to find the coding efficiency. So in order to find the coding efficiency, we need to have the entropy and average code word length. So let us find out that the average code word length L is nothing but some summation of Ni and the Pi. So ni values are listed here. For every symbol, we have 5 symbols here, and probability values are also given here. They all have the equal probability. So we multiply them once here for all those ni values, and that becomes the average code word length 2.4 minutes per system. And then we need to find the entropy of the source. The entropy is given by this equation, summation of pi log 1 by pi. So that is straightforward here, 2.32 bits per symbols. And finally, we find the coding efficiency, which is h of x divided by L log R. Again, we use a binary coding. We use the coding as 0 and 1. So log R becomes 1. So basically, coding efficiency is h of x divided by L. So that comes to 96.7%. So the question we have, in the question we have another part, that is, try to perform Shen-Fan encoding using any other ways of grouping. That is the second part of the question. So we may have another solution here, because while solving the first question, we notice that there are different ways of grouping possible. For example, so we have all the probabilities listed here. Now, in this case, that is another solution would be to consider these two elements in one group and these three elements in another group. Earlier solution was forming the first group with three elements, but now we are forming the first group with the two elements. The total probability is 0.4. This probability is 0.6. They are nearly equal. I mean, we cannot do a better division than this. Okay, so the top group is assigned 0, bottom group is assigned 1. Now, here, can we divide them? Yes, of course. We can divide these two elements individually as 0.2 and 0.2. And similarly here, we have these three elements. We can divide them, maybe two elements in one group and one element here, or one element here and remaining two elements in another group here. And now we assign the coding to them. So 0 goes here. The top element is 0, bottom element is 1. And now for this being divided as two groups here, so this 1 will be carried here, 1. The top group is assigned a 0, bottom group is assigned a 1. Okay, so when we see these three groups, no further division is possible, but this group we can divide further. So we will do that division here in the third stage, and we will continue the coding. That is 1, 1 becomes here as well as here. The top group will have a 0, bottom group will have a 1. So this is the coding scheme that we use. So S5 has X5 has 1, 1, 1, X1 has 0, 0, and so on. So these are the NI, the length of the code words here, 2 bits. So value is 2 here, is 3 because there are 3 bits here, and so on. Now we need to find out the average code word length. So equation is Ni multiply Pi. So since the probability values are same and also the code word length in this case also same, we have 2.4 minutes per symbol. Next, the entropy values, of course, depends on only on the probability. Since the probability values are the same, so we will have the same entropy, that is 2.32 bits per symbol. And then we have the coding efficiency. So we are comparing the coding efficiency here. So the coding efficiency of this is 2.32 divided by 2.4, that is 96%. So in our comparison with the previous case, there also it was 96.7%. Even in this case, it is 96.7%. That means we used different ways of dividing the symbols. I mean, in the first case, we had three elements or three symbols in one group. In the second case, that is in this example, we considered two elements in one group. But in this case, the performance remained same, irrespective of the grouping we adopted. Okay, now we'll move on to another example here. So this says a DMS, I mean memoryless source, discrete memoryless source produces two symbols x1 and x2 at its outputs with the first probability, I mean the probability of the first symbol is 3 by 4 and probability of the second symbol is 1 by 4. Now design a suitable code using Shannon-Fano encoding algorithm such that the efficiency is at least 85%. So this is the question with a different requirement here. So in the previous questions, we were asked to find the efficiency, but in this case, the efficiency is given. So we need to design a suitable coding scheme so that we meet this requirement. So this is more challenging. So how can we do that? Let us try to represent these probabilities in terms of and get a coding scheme using Shannon-Fano encoding method. And then we will see what is the performance. So if we cannot reach the performance, then we need to do some intelligent methods to achieve that performance that we will see in this case. So right now we have two symbols and their probabilities listed in the non-increasing order. So right now we have the code word for since there are only two elements, we just can divide in only one way. That is one element here, and the second group will have second element here. The top group will have a value of 0, bottom group will have a value of 1. So this is the end of formation of codes or formation of groups. So the first one has a code word of 0, second one will have a code word of 1. And ni is nothing but 1 because we have just one bit in each of these code words. So this is the end of Shannon-Fano encoding scheme. Since there are only two elements, we have to do just the division once. That is, we have to make two groups. We made the two groups here, group 1, group 2. Top group has a 0, bottom group has a 1, and that's it. We cannot do any more grouping. Yes, then we find the average code length, that is ni and pi. Ni multiply pi, that is 1 minute per symbol. Then we find the entropy, that is pi log 1 by pi for both, that is 0.8 bits per symbol. So then we find the coding efficiency. This is nothing but h of x divided by L. So h of x is 0.812112 and this is 1. So the coding efficiency comes to 81%. So you notice that 81% is lesser than 85%, which was the requirement. So now, using the given symbols or the given probabilities, we cannot achieve 85%. So we need to adopt some intelligent methods of transmitting the symbols. So we will do that. We need to do some modification to the symbols that we can transmit. So how to do that? Watch carefully here. So the hint is, since the efficiency is less than the required 85%, we need to use some intelligent ways of representing the probabilities. How to do that? Let us extend the system to second order. That is, instead of sending just one symbols, we will group them like x1 and x1, x1 x2, x2 x1, and x2 x2. That means we have two symbols. We will make from these two symbols we can have four combinations. First and second symbol, first and first symbol, first second, second first, and second second. These are the four combinations we can do. And then basically we are trying to transmit in this way two symbols at a time. And We will find the probability for this, for each of these four symbols, and then check whether can we achieve the efficiency of 85%. So when this is called as a second order system, because instead of sending one symbol, we are sending two symbols. So when we send the two symbols, the probability of the first combination, the first symbol and first symbol is probability of 1 and probability of 1. That is nothing but 3 by 4 multiply 3 by 4, that is 9 by 16. The second combination is probability of 1, probability of 2, that is 3 by 4 multiply 1 by 4, that is 3 by 16. Similarly, 2 and 1, this is same as here. And finally, the fourth combination, sending two symbols here, that is a last two symbols. I mean, second symbol and second symbol, their probabilities are P2 and P2, that is 1 by 4 multiply 1 by 4, that is 1 by 16. So this is the extended version of one or first order system. Instead of sending one symbols, we'll be sending two symbols at a time. So now, since we have four symbols here, their probabilities are arranged in this way. And then, that is, this is the highest and this is the lowest. It's a decreasing order or non-increasing order. And then we need to divide them into groups, two groups. So which is the best way of dividing so that their probabilities becomes almost equal? So if we divide these three as shown here into one group, the total probability becomes 3, 6 and 7, 7 by 16. And here this has another group, it is 9 by 16. So they are almost equal. So we will put this element into one group and these three items into another group. And we will label it as 0 and 1. And the same process continues. We cannot divide this again, but we can try to divide this into two groups. How to do that? Either we'll put this one in one group. Yes, we'll put this one in one group and these two in another group. And we will assign a 0 and 1 here. This cannot be divided, but we can divide these two. Of course, the boundary should be here because one element should go to one group, another element should go to another group. And the top element will have a 0, bottom element will have a 1. So further grouping is not possible. Right now we have all groups having just one element. So this is the end of Shannon encoding, and we will see, and these are the code words that are generated or assigned to different symbols. Yes, here that is shown, and NI is the number of bits in each code word, 3 here and just 1 bit here. And then we will find the average code word length, that is summation Ni Pi. So you know the values of Ni. In the previous slide, we have found the values of Ni, and also we know the values of probabilities, that is P1 P1, P1 P2, P2 P1, and P2 and P2. Okay, so this is the average code word length. Then we'll find the entropy. We already know from the Shannon's algorithm that h of x square, that is for a second order system, the entropy is nothing but 2 times the entropy of the first order system. So we have already determined what is the entropy of the first order system in the previous case. It was around 0.8. So multiply by 2, it becomes 1.622 bits per symbol. And then finally, we will go to find out what is the coding efficiency. So coding efficiency is nothing but the ratio of h of x by log r and multiply by L. So that comes to 96%. So the requirement was 85%. So we have achieved a better efficiency in this case if we can extend the first order system into second order system, because that was the requirement. So this is how we can achieve the minimum required coding efficiency. So this is the end of this example as well as end of today's discussion.